Alright, we're going to start our new section here on polynomial and rational inequalities. Now we did study polynomial and rational equations earlier in this chapter, and we did do some discussion of linear inequalities way back in a previous chapter. So what we're going to do is kind of combine some of that information to solve polynomial and rational inequalities. We'll start with polynomial inequalities. Now, a polynomial inequality is f is a polynomial, then an inequality of the form where f of x is less than 0, f of x is greater than 0, f of x is less than or equal to 0, or f of x is greater than or equal to 0 is called a polynomial inequality. So it's going to most likely look like a polynomial equation, with the exception that instead of an equal sign, we'll have one of these inequality signs. Now, to solve a nonlinear, and I say nonlinear because linear inequalities or polynomial inequalities, a very special kind. We're going to look at mostly those polynomial inequalities of degree 2 or higher. My suggestion is to rewrite the inequality, step 1, so that one side is 0. So bring everything to one side, have one side equal to 0. Then I would solve the inequality as if it was an equation. If it's quadratic, you might have to use factoring or the quadratic formula. If it's higher degree, you might hopefully have to use factoring, or maybe just issue the rational root theorem or the rational zero theorem. But you need to find the values that make it equal, because these solutions to the equation are key values that we're going to put right on the number line. And of course, once we put some points on the number line, we're going to have intervals that are formed. We're going to test each interval to see if it makes the polynomial greater than 0 or less than 0. Makes it positive or makes it negative. And I'll put a little plus sign if it makes it positive, a little negative sign if it makes it negative in the interval on the number line, because I'm going to use that to create my solution. Okay, now it also says the boundary points. I think I just wrote bound, but the boundary points, which are the key values there, the points that are graphed on the number line, are used if the inequality sign is greater than or equal to, less than or equal to. It's kind of like the filled in dots that we used to do back in our Algebra 1 days. And if they don't have the equal to part, if it's just a greater than or less than, then we're not going to include those boundary, let's see if I can sneak that in there, boundary points. And then once we have this all sketched out on the number line, we're going to use that number line and we're going to write our answer in interval notation. Now I have an example up here. This is a quadratic, and I have 0 on one side. If I graph y equals x squared minus 3x plus 2, which I did in this kind of brown looking parabola here, do you see at times your graph is above the x-axis, your graph is on the x-axis, or your graph is below the x-axis? If I want it to be less than or equal to 0, graphically, I'm looking to see when the y values are less than or equal to 0, because y is equal to that. When is y less than or equal to 0? Well, that happens right in here, between 1 and 2. So my answer here, I would write, would be all the values of x between 1 and 2. Now you say, well, I don't want to have to graph these things every time I solve an inequality. I want to go perhaps and use these steps to help myself out. Well, that's what I would do. I have 0 on one side. In this case, I can factor, because I'm going to solve it as if it was an equation. And that would be x minus 2, x minus 1. So my key points that are set up, my boundary points, are x equals 2 and 1. So I draw out my number line. I put those two key points there. You don't have to put a whole slew of points on your number line. And I test these three subintervals. I take a value from here greater than 2, like 10. If I plug 10 back into my inequality, or back into this expression right here, just kind of ignore that. 10 minus 2 is positive 8. 10 minus 1 is positive 9. Positive times positive. I would get positive values here. Take maybe 1.5. 1.5 minus 2 is negative. 1.5 minus 1 is positive. Negative times positive is negative. Take a value like 0. 0 minus 2 is negative. 0 minus 1 is negative. Negative times negative is positive. And that matches up with what I have up here. Do you see less than 1? It's above the x-axis. It's got positive y values. Greater than 2 over here, it's above the x-axis, so the y is positive. But between 1 and 2, these values here, it's negative. Now remember what I said. we keep the boundary points if it has the equal to, and this one has the equal to. So instead of putting filled in dots, what I'm going to do here is I want when it is less than or equal to 0, I want when it's negative. So I'm going to include the boundary points, and I'm going to graph it right on the number line. That tells, this is set builder notation, but that tells me in interval notation that my answer is from 1 to 2. Now, it's nice if you have a sketch, and in some problems they'll give you a sketch rather than give you the inequality, and they'll ask for you to solve. And you just look to see when it's above or when it's below the x-axis to figure out if it's less than or if it's greater than. Now here's one where they don't give you a graph, and they ask for you to solve the inequality. So I'm going to do step number 1, is I'm going to try to rewrite it so that one of the sides is equal to 0. I'm going to distribute. I have 2x squared minus 2x is less than 21 minus x. I'm going to subtract 21, and I'm going to add x to both sides to get everything over here. So 2x squared minus 2x, I'm going to subtract 21, and I'm going to add x to both sides. So that these will cancel out, and I will get 0 on one side of my inequality. Over here I do have some like terms. I have 2x squared minus x minus 21. Now, here's where we solve this as if it was an equation. I'm going to solve this as if it was an equation by factoring. So if I set this equal to 0, I would have 2x, hopefully it'll factor, and an x, and I think it does. Put the 3 here, put the 7 here, minus here, plus here. And those key values that I'm looking for that make it equal to 0, that would solve the equation, are 7/2 and -3. So what I'm going to do here is I'm going to draw a number line, and I'm going to put down those two key values. And I have 3 subintervals. So I pick a value from each one of these. Let's say I pick a number over here like 10. 2 times 10 minus 7 is positive. 10 plus 3 is positive. Positive times positive is positive. Take a value in here like 0. 2 times 0 minus 7 is negative. 0 plus 3 is positive. Negative times positive is negative. Take a value over here like negative 10. 2 times negative 10 minus 7 is negative. Negative 10 plus 3 is negative. Negative times negative is positive. Now you say, oh, I get it. Just like the last example. If there are two key values, it's plus minus plus. Not always. Sometimes, but not always. You do need to test the intervals. And kind of depending on the multiplicity of some of these values, they may not alternate signs. They may go plus plus around a key value. So be careful on that. Now I want where it is less than 0. Less than 0 means that it's negative. So I want this, but I don't want the key values. I don't want the boundary points. So I am going to use parenthesis, parenthesis, and everything in between. Now, I draw all of this out on my number line so that I can easily write my solution set in interval notation. And as you can see, my interval notation is from -3 to 7/2. And that is my solution. Alright, now this next one's got a little bit of a boom to it because it's a quartic. You can see x to the 4th. I'm not used to doing a lot of work with quartics and such, but we'll go ahead and we'll follow the steps, and we might have to use the rational zero theorem. We'll see what happens. So the first thing is I'm going to get everything on one side so I have 0 on the other side. And to do that, since the x to the 4th is my highest degree term and it has a positive coefficient, which I like, I'm going to subtract 3x squared and add 4x cubed to both sides. Now I'm going to be really lazy here. I'm going to add 4x cubed to both sides, so I'm going to write it next because it's descending order. And I'm going to subtract 3x squared from both sides. So I'll write it next, and then minus the 18x. And then of course everything over here, if I've done it right, should cancel out. And I should get 0. Now here, before I write it again with a 0, I'm going to notice here that I can factor out a Gcf of X. Kind of combining some steps here. There's my 0. Now, don't divide both sides by x. You're going to lose this key value here. So what I'm going to do next is I'm going to try to factor this 4-term polynomial, which the only way I know how to do that is by using grouping, and this is not going to group well. So I'm going to have to do a little rational root action here. So p could be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 9, plus or minus 18. Q can only be plus or minus 1, so p over q would be those values. And I would go through the process with a 1, a 4, a negative 3, and a negative 18 to see if it works for 1, to see if it works for negative 1, to see if it works for 2, to see if it works for negative 2, until I get 1, because as soon as I get 1, I'm going to end up with a depressed polynomial that's quadratic, and hopefully I can factor, use the quadratic formula. It's been a while since I've done this problem, but for some reason I don't think it works for 1. I think it works, or negative, I think it works for 2. Let me see here. Well, that's a 1. I hope I got this right. That's a 2, that's a 6, that's a 12, that's a 9, that's an 18. Sometimes I just remember that kind of stuff. So this is going to give me a remainder of 0, and my depressed polynomial here is x squared plus 6x plus 9. So that gives me x times 2 here, x minus 2, times x squared plus 6x plus 9. You may have already noticed, that's a perfect square trinomial. That's x plus 3 squared. So now I have it exactly in the form that I want. I'm going to solve this like it was an equation. So over here I have x times x minus 2 times x plus 3, quantity squared equals 0. Well, that happens when x is 0, or x minus 2 is 0, or x plus 3 is 0. So that happens at 0, at 2, and at negative 3. Those are my 3 key values. Draw that number line out. And I have negative 3, and 0, and 2. Make sure you put them in the right order. Take a value from each one of these intervals. I'll start with the biggest. I'll take 10 from here, so that's positive. 10 minus 2 positive. 10 plus 3 quantity squared positive. Take a value from here like 1. That'd be 1 plugged in there is positive. 1 minus 2 is negative. 1 plus 3 squared is positive. Positive times positive is negative. Take a value from here like negative 1. That would make that negative, negative 1. That would make this negative. Negative 1 minus 2 is negative 3. So negative times negative, and negative 1 plus 3 quantity squared. Since it's squared, it's going to be positive. So negative times positive is positive. And you can see it looks like it's just going to alternate. Why bother plugging in another number? It's just going to end up being negative, right? Well, let's try. Negative 10. Negative 10 in there makes that negative. Negative 10 minus 2 makes that negative. Negative 10 plus 3 is negative, but it's squared. So this is positive. Negative times positive is positive. Notice, double or multiplicity 2 here at negative 3, and the signs don't change. That's food for thought. If you have multiplicity even, the signs won't change. Multiplicity odd, they will. So I want where it's greater than or equal to 0. That's when it's positive. So here, here, and here. Let me grab another color pen here. Because of the equal to, I want to include all these. So I would include all the values less than negative 3, which would look kind of like this. And then all the values from negative 3 to 0 inclusive, which would look like this. So since these are both brackets, you don't really need those brackets. So it's everything this way. This is negative, I don't want that, but I want everything from 2 on, because that makes it positive or 0. So my interval notation solution to this inequality, this one's a peach, goes from negative infinity to negative, almost a negative 3 because I was looking right at it, to 0. I don't need the negative for 0. And, holy smokes. All right, and of course it smears that much worse. Including 0, and then from 2 on, including the 2. And there's your solution set. Now, this one took a lot of work. I had to use the rational root. I had to help break this down, but I wanted to get this into factors to find my key values as if I solved it as an equation. And then once I had those key values, I can test the intervals on the number line. All right, this very last example here is talking about special cases. And you'll notice I have the same exact quadratic polynomial here on the left, and then different inequality signs 0 on the right. The reason I did that is because this guy right here is a perfect square trinomial. This is 5x minus 1 quantity squared less than 0. This is 5x minus 1 quantity squared is less than or equal to 0. This is quantity 5x minus 1 quantity squared is greater than 0. And then this one is 5x minus 1 quantity squared greater than or equal to 0. And you say, well, why are they special cases? Because it's the same factor. It has to do with that kind of that idea with the multiplicity 2. Now think about this though. When you square something, it's non-negative. The smallest it can be is 0. If I have 1/5, for example, x is 1/5, it's 0. But it has to be less than 0. Well, you can't make non-negative less than 0. So there is no solution here. And in this example, you say, well, it can't be less than 0 here, it can't be less than 0 here. That's true, but it can equal 0. Remember, it's just that at 1/5, 5 times 1/5 minus 1. So this has one solution of 1/5. You just take the 5x minus 1, set it equal to 0. On the other hand, since it's not negative, that means it's positive or 0, so the quantity 5x minus 1 quantity squared greater than 0 sounds pretty good for a lot of numbers. Because no matter what you plug in, it's going to be non-negative. The only one you'd have to exclude is 0, and that's 1/5, so it'd be everything but 1/5. Can't have 1/5 because that would make it equal to 0. So from negative infinity to 1/5, parenthesis, union, parenthesis, 1/5 to positive infinity. And last but not least, the quantity squared greater than or equal to 0, well, that means it would be non-negative, because any number that you plug in makes this expression non-negative, which means it's greater than or equal to 0. So for in this last special case, it goes from negative infinity to infinity. So these don't pop up all that often, but if you see that you have this quantity squared set up this way, where you have a perfect square trinomial, for example, then remember you do have special cases to consider.